honorable guests, ladies and gentlemen. My name is Mats Holmberg, and I'm responsible for public affairs in ABB Northern Europe. I will talk a little bit about our history. And this is a picture of the history. Now, you won't understand what it says because it's in Swedish, but it's an advertisement from 1885, something like that. And it's a company called Wenström and Granström, electrical power company. And they are talking about electrical power transmission, electrical railroads, electrical lines, electrical bleacheries for pulp, drilling machines for mining, electrical elevators, and so on and so forth. And they have very good references. And you can also see there are two pictures there, one of a motor and one of a generator. And they seem to be exactly the same machine, and that's how it all started. Two persons, two brothers, Göran and Jonas Wenström, where Jonas Wenström was the inventor. And he invented, again, a dynamo about this time, 1880, something like that. There is a story that he actually started to develop a light bulb. But during a trip to the United States in the 1870s, he met a person called Thomas Alva Edison. And he found out that Edison was much further in his development of a light bulb, so he gave it up. Mr. Wenström established, together with another man named Gustav Granström, a company in an attic in Arboga. So that's how it all started, basically. They have this product, the dynamo, which they were trying to sell. Around the same time, another person in Stockholm, who was a banker, had actually got some money out of a bankruptcy and established an electrical company. And the reason for that was that he had seen street lights in Germany and found that that would be very suitable in Stockholm. So he decided to start an electrical company. But it wasn't until a couple of years later when actually Gösta Wenström and Göran Wenström, and Ludwig Freiholm actually met, and they merged the two companies together to Allmänna Svenska Elektriska Aktiebolaget, or if you translate it to English, General Swedish Electric. And that was happening in 1890, but actually the company originated from 1883, from the Elektriska Aktiebolaget. They moved to Västerås, which is about 30 kilometers away. And the reason for that is actually the picture in the bottom of these four pictures. Because in Västerås you found a municipality. The chairman of the municipality was called Godfather because he decided everything in Västerås at the time. And the brothers Wenström, they wanted to explore power transmission. And for that they needed more power, so they wanted a hydropower plant. So the municipality actually built this little power plant in the middle of the city center of Västerås. It's still there today, it still works today. And for that reason they moved to 30 kilometers. And I think the municipality in Arboga today are not exactly happy of what was going on in the 1890s. Then we're coming into an issue which we heard in Mr. Kolk's presentation here, where he talks about the inventor, the invention as such, and then the entrepreneurship, and then the market. And what we have talked about here is actually two of the three. We talked about the inventor, we talked about the entrepreneur, the financial endurance to be able to develop something. But then we talk about the third thing, which is the market. And in the end of the 1880s and beginning of 1890s, we had a mining industry built up in Sweden. And the mines at that time was manually operated, totally. One of the biggest problems is the water levels in the mines and how you can evacuate that water from the mine. And it was normally done by manpower. People were carrying water in buckets, up ladders from the mining to the surface. And they thought they could use these dynamo as a generator and as a motor to drive pumps, to make it more efficient. So Wenström then thought, well, he needed more power to do that than what was used so far because of the level. The amplitude of the water has to be pumped from the mine to the surface. So he started to develop the three-phase system. And out of that, get more power into this motor. And in 1893, the first commercial three-phase transmission system was in operation. It was not very long, 15 kilometers, as you can see, 300 kilowatts, which is nothing with today's figures, and 9.5 kilovolts. The actual power plant is the one you see on the second lowest picture, the control panel for that. It is very close to Ludvika, this place, Hällesjön. And Grängesberg, that is a place about 15 kilometers away from there. So that's how it all started. We had the inventor, we had the entrepreneur, and we had a market. At the same time, roughly, two persons in Switzerland, a Brit and a Swiss, also met and basically went through the same story. Charles Brown and Walter Boveri established a company called Brown Boveri Company. They went on a little bit different path. They were into the production, and as in fact the first combined cycle type of power plant producing alternate current was built in Switzerland in 1891 by BBC. Things that we take for granted today was done by visionary people in those days. To continue this, the mining company in Gränge in Sweden, they thought that this was good business, so they started their own company, producing motors for the mining industry. It didn't go very well because the market was too small, basically. There was only a few mines and so on and so forth. So in the end, ASEA bought these in 1916. Before that, we have also in Switzerland seen a development of making this power plant more efficient by introducing the steam turbine. And this, as we will see, would follow but several steps later into the gas turbines and so on and so forth. These two companies was in 1988 merged into one, which is today known as ABB. The same story in a bigger perspective, perhaps. If you look at the developments, and here we have only looked at very few, really, of what we have done over the years. You can see that on the upper side of the timeline here, we have the Swiss development, and on the lower line, we have the Swedish development. But we can clearly see that we have done a little bit different journeys between the two companies over the time. We have up on the left-hand side, we start in the 1900s, we have the steam turbine. We have the power plant or the hydropower plant in Sweden, which was then connected to the mines. But we also go into further developments. We were not happy with that, or they were not happy with that. They started to develop turbochargers to make the steam turbines more efficient. To develop the several steps of a turbine, the combustion part and the compressor part. So the turbochargers was a very early development in this. In Sweden, we started to develop electrical trains. 1925, the first electrical train line was inaugurated, which was between Gothenburg and Stockholm, with ASEA engines in there. The same design, as you see on this picture here, was used all the way up to the 1980s. They changed from a wooden carriage to a steel carriage, but otherwise they look exactly the same. Of course, the electrical system inside was different. Then, of course, the steam turbine was not enough. The demand for electrical power increased. So the people in Switzerland started to look into other ways of producing electricity. So they came up with a gas turbine in the end of the 1930s. Gas turbine which with many factors improved the performance of this. In Sweden, we also invented a transmission transformer. The first one was installed in Stockholm, and it was actually in operation for many, many decades. And it was installed in 1935, 120 MVA, 220 kV transformer. A big step in creating a transmission network. Because the electrical system has, since those days, been a radial type of history. We have a central production and then a long transmission line down to the populated areas where the consumers are located. Also in Switzerland, we started to develop trains. And actually, this locomotive, which is seen here in 1944, 43, something like that, is a high-speed train. Maybe the first in the world, we don't know that exactly. But it is a high-speed train. It could do more than 200 kilometers an hour in those days. And they had a very ingenious drive package in it where the axles in the bogie was directly driven by the motors. We also started to develop cables because we saw that these long transmission lines were good. But when we came into the cities, it wasn't very convenient to have these type of overhead lines all the way into the populated areas. So we built, we had a factory in Stockholm, which is nowadays located in Karlskrona. And in 1950, we produced the first 400 kV cable for underground installation. Another very significant part of the transmission system is to know the status of the system. And here we have also been a pioneer in developing communication media, where we have used frequencies, higher frequencies, on the actual power lines to communicate between outstations and a control room. And these high-frequency carriers was used in 1953, something like that, in Switzerland on 700 kV connection, test connection, but still demonstrators, but still operating. It's still a product today. We are delivering, we can say that about 30% of all transmission lines in the world have this type of equipment today. 1954 was a significant year for ABB, because that, and the world as such, because that was the first commercial HVDC line. HVDC, to actually build direct current on high voltage, was invented by a person called Uno Lam, actually in 1928. In 1928, this type of system was developed. And still, it took to 1954 before the first commercial order came. And there we can talk about this entrepreneurship, the endurance you need sometimes as an inventor before things are happening. This line in 1954 connected the island of Gotland to mainland Sweden. But it's basically, essentially, the same technology as used in Eastlink between Estonia and Finland, or Nordbalt, which is between Lithuania and Sweden, which is under construction right now. We have gone several steps in this area, and I will come into some of those steps later on, which is the latest development in HVDC. But it is a fantastic evolution in terms of energy efficiency, of transporting bulk energy over long distances. Another thing which is perhaps a little bit out of scope when we're talking about electrical power and so on, was that ASEA in the end of the 1950s developed a Quintus press, a unit which at a high temperature and high pressure could fabricate things like industrial diamonds. We were actually the first in the world to produce industrial diamonds with this press. It's no longer within ABB, it's sold the whole thing, but it's still a world's first, which has been quite important in many aspects. We invented the gas-insulated switchgear in the 1960s. Substations have always been a big part of our business. We started with that as a part already in 1893, and that has continued. And gas-insulated was again a way of be able to put substation in populated areas. We could decrease the size with 70%. We can put it in-house, which means it didn't show to people, because they are not very nice to look at normally. We also started to produce thyristors, high current thyristors, and that was essential to be able to go to the next steps. With this, we started with something what we call today FACTS, flexible AC transmission systems, where we use power electronics to increase capacity on existing transmission lines, sometimes with up to 50%. This has been essential in many countries where it is difficult to get permissions to buy new transmission lines, where you can use this instead to increase the capacity on the ones you already have. It also gives some other effects. It produces it's a sort of a filter to the grid for for intermittent power sources or intermittent disturbances, like, for instance, intermittent sources like wind power, where you put equipment like this before you connect it to the grid to be able to filter away noise and disturbances to the grid. Another application could be steel mills, where furnaces are producing a lot of noise, and you don't want that to put out on the grid, so you put this type of equipment in there instead. A very significant business, which today is very much in focus in terms of energy efficiency. We also worked with motors from the start, and we had several steps in being more efficient with this. And one of these inventions was a gearless motor drive. I don't know if some of you remember the old DAF car, where you had a belt drive, which sort of changed according to your speed seamlessly, it felt. This is a similar design, not with belts, but it's still a gearless drive, which means you can adjust the speed without having a gearbox attached to it. Again, a way to be more efficient. Network management, to be able to control the grids, because the grid started to be so big in the 1970s. And again, we had another invention which we could use for this, the microprocessor, which became more accessible to people. The prices came down a bit. We could start to use this to control, supervise our transmission grids. We have thousands of these type of systems in operation today. Upgrade them, we are expanding them, and so on and so forth. Another very ingenious invention, which we will hear a little bit more about later on, is the industrial robot, which was invented by ASEA in 1974. A device which can handle work where people perhaps not normally would like to operate, at least not for long times. We can also save energies with this. Maybe Anders can confirm it later, but I've heard figures saying that a paint robot can save about 50% of the paint compared to human beings standing there spraying the paint on a car, for instance. Variable speed drives, that was the next step. Variable speed drives, again with the power electronics, where we, with the power electronics, can change the speed of a motor with full torque or also with an applied torque. How did we do it before? Well, we had gearboxes, or we had mechanical brakes. Or, for instance, if you have a fan connected to the motor, we are normally adjusting it by the flow of the wind or the flow of the air through the fan. We don't control the motor. Now we can start to control the motor. One example is Heathrow Airport in London. Terminal 5 installed the whole ventilation and AC system with this type of equipment. The whole equipment was repaid in less than 2 years because of savings in the energy bill. Amazing achievements, really. In 1988, as I said, we merged BBC and ASEA into ASEA Brown Boveri, which is then short for ABB, and nowadays it is ABB in most countries. This is from the signature ceremony. Some of us who are here today representing ABB was actually in the company already then, but I don't think any of us participated in the signing though. New developments over the last few years has been the propulsion systems for marine vessels, the AZIPod, the azimuth electric podded drive, which is a unit where you mount underneath the ship. It is rotating 360 degrees on its vertical axis. It contains the propeller, of course, but also a very high efficient electrical motor. And then you have a drive package, variable speed drive package, up in the ship itself. And with this, you can gain a lot of savings in energy, but also high maneuverability, because you can turn them 360 degrees. We have this in the biggest cruising ship today, for instance. We have it on oil platforms to be able to move them around. We have them on other types of ships as well. I don't know an exact figure, but it's in the hundreds of vessels that have this type of installations. The extended control system is worth to mention. Control system for process industries. Here, we also today is not only controlling the actual process of a paper mill and so on, but also how is it driven? What type of energy do we have for this? How are we using that? We can control the electrical system. The introduction of IEC 61850 protocol for communicating with electric devices means that the entire plant can now be connected into one system. Also worth mentioning for this extended control system is cranes, for instance. Cranes in harbors, where we just recently have got huge orders from harbors over in South Korea, for instance. The entire harbor is going to use this system, where one operator can oversee the entire crane operation in the harbor. And then ultra-high voltage DC, which is the next step. We have delivered a system in China for 800 kilovolt DC, where we transmit 6,000 megawatts over 2,000 kilometers from the Three Gorges and down to Shanghai area. And I'm going to show you an example of another of these projects later on. So this is our history in terms of development from the beginning until today. How can we utilize this? How is this important for ABB, this history? Well, we are very much aware of that if we don't know the history, we don't know where we're going. We know where we're aiming at. We are living in a world today where a lot of things are happening, politically, financially, and so on. And all this is directing us for the future. This history is, of course, something we can we can utilize. You can see that a lot of these things we see here in the bottom of the timeline is actually things that has been further developed from earlier inventions, earlier innovations. Power electronics has been a major part of this. Robotics is a major part of this. And of course we can build all this together. The extended control system with industrial robots, with the variable speed drives, and so on and so forth. And this is of course extremely important to be able to do this, to have the complete package. This is ABB today. We're 135,000 people. We have revenues of about $38 billion last year. We are operating in more than 100 countries today under our own banner, and we are a publicly owned company. R&D is an essential part. As you have seen, it's been an essential part of us already from the start. We are investing about $1.4 billion every year in R&D. We do this in many ways. We, of course, have corporate research centers around the world. We have 7 of them, all in total. But we also do developments in our actual business units itself. And that's something you will hear about also in a few minutes' time. Altogether, we have more than 7,000 scientists and engineers working with us. And we are collaborating with a lot of universities, of course. This is, of course, our competitive edge. We always want to be in the forefront of the technology, and we believe we are in the forefront of the technology in most of the areas where we are operating. Today, our life is driven by megatrends. This is a picture taken out of our strategy which we launched in November last year, where we have identified 7 megatrends in the world: environment, urbanization, growth economies, the various power shifts we have seen around the world, electrification, of course, digital information, transports in various forms, and last but not least, resource economy. We see that energy efficiency is an important step. If we're looking into what's driving a lot of our business today, it could be said out of this picture: energy efficiency. If we are going to reach the 450 policy scenario, which means that the CO2 emissions will stay at a level where we will only have 2 degrees centigrades of increased average temperature around the world. The biggest part, 72%, comes from efficiency. 72%. Now this is in total in energy, and as you know, there are 7 different types of energy, and electrical energy is by far the most efficient. So that's why electrification is a mega trend. We see very clearly that even though demand of energy is increasing, the demand for electrical energy is increasing even more. So efficiency would actually do more for the global environment than renewables, which will stand for 17% of this change. So a lot can be done. But there is also a lot to do still. This is how we see the future sustainable society, where you can find the old hydropower plant far away from the populated areas, where we put wind power also far away, sometimes not even onshore, we put it offshore. And offshore wind connections, there we today can use, for instance, HVDC, which we're doing in the North Sea. We build an oil a platform, basically, put it out by the wind park, build an HVDC conversion station there, and then bring the whole energy flow with one cable in onshore, convert it again to AC and connect it to the grid. We're also using this to connect countries together. We have seen all these links popping up. East Link, we mentioned before, Nordbalt, we have others. Norway, Holland, which is in a way a very interesting project. Norway to Netherlands, it's 580 kilometers, the world's longest sea cable, delivered by ABB. In Norway, they have pump power plants, which means that you can let the water through the turbines, produce electricity, but then you have pumps to pump it back up again in the reservoir. What they do is that Holland has shortage of energy during daytime. So during daytime, the Norwegian hydropower plants are producing electricity. The electricity is shipped through the sea cable to Holland. Holland has wind power. During nighttime, when they don't need it, they send the energy back up to Norway, where they're using the energy to pump the water back up again. It's actually net zero transmission over that line, over 24 hours. Very brilliant way to utilize this type of technologies. Of course, solar power and wind power and local production and things like that are happening very much now, which means that the whole transmission system as such will change as well. And this is, of course, also something which puts a lot of challenges for politicians, for grid operators, for all different parts in the society, and of course also for us, the suppliers. And again, R&D is a very important part of this. In a way, we can lead the way, and we are leading the way in that sense, to come up with solutions, proposals. We can do this, we can do that. I think when we come to energy efficiency, we can solve all these issues today if people are just starting to look at CapEx, OpEx, and so on and so forth. As you can see, everything we have done since 1891 is basically energy efficiency. We started with man carrying water in buckets, and we put in motors instead because it was more energy efficient. So we have done that since the start. We can do that today as well. LKAB is the biggest Swedish iron ore company, mining company, in Kiruna in the north of Sweden. They were going to replace 25% of their motors. And they were typical motor installations, motors with mechanical brakes, with gearboxes and things like that. So we said to them, well, why don't you change all the motors and you put in variable speed drives instead? And they said, well, it's a much bigger investment. Why should we pay 5 times more for this? You know, we would have to go to the board of directors to ask for an approval and so on and so forth. And we said, yeah, but you will save a lot of energy. You will actually pay off this investment in less than 3 years compared to what you have today. So they went for that. And actually, they repaid it in 2.5 years, the whole investment. But it comes to, of course, a situation where you have to look at what you got and what you can get, and start to look outside the boundaries to see the effects you can get. I'm not saying that that will happen in all cases, but when it comes to variable speed drives, you can say that we do savings of 25–30% in most cases, up to 50% in some rare cases of the energy bill. Will the energy price as we have today stay for long? Most people don't think so. Because when we start to unite the markets, and there will be, will mean, and investments that have to be made in the transmission system, the energy price will probably go up. That means the energy efficient will be even more profitable in that future. So this is how we see things. Of course, the local production is also interesting. We as consumers, because we are also all consumers. We have, for instance, solar cells on our roof in our house. And we can sell that back to the utility. Or we have an electrical car in the future. We can use the electrical car as a storage, electrical storage. Again, R&D is vital in all this. Battery technology. All these sorts of things that comes up nowadays and is so important for the future. In the industry, however, this is perhaps even more interesting. Light bulb, as you might know, is perhaps the biggest consumer in residential areas, in our houses. In Sweden today, it's not allowed to sell light bulbs. I've heard there is a hole in that law there. You can, if you go to the suppliers and tell them that this is for industrial use, you can still buy them. But for residential use, you cannot. The light bulb of the industry is the electrical motor. Those are, and the interesting thing about the electrical motor is that 90% of the life cycle cost is the energy cost. It is not the purchase price. It is not the installation. It is not the scrapping of it. It's actually the energy cost, which is the biggest cost over the life cycle. So, of course, there is a lot to do in this area. Now you think, of course, that in ABB we have changed all our motors to these type of things. No, we haven't. We are not better than anyone else. But we are on the path of doing it, at least. But there is a lot to gain from this. We talked about before mega trends, and we also talked about ultra-high voltage DC. This is the latest project we have in ultra-high voltage DC. I talked about this one in China. This is a later one in India. And this is typically for the mega trends, that we see this type of projects coming up, where mega trends are driving the whole thing. Urbanization. This project in India, you see the two hydropower plants up on the right-hand side in eastern India, or in Kashmir area, producing a lot of energy. But there is not a lot of population up there. The population is down in the Delhi area. And Agra is just outside of Delhi. Agra is actually where Taj Mahal is located. It's about 1,700 kilometers away. And of course, there is an enormous amount of people in the Agra area who could utilize this. I don't know if you read 3 weeks ago, there was a major power cut, blackout, in exactly this area. One power cut, 640 million people were affected in one cutout. And the blackout lasted for more than a week. More than a week. The Minister of Energy got sacked. Why did this happen? Well, it happened because local government allowed new businesses to be built, which increased the demand to a level where the grid system couldn't cope anymore. This link is going to be built exactly to help this. The two hydropower plants up in Kashmir is producing today about 6,000 megawatts. That's equivalent to 12 nuclear reactors. All that energy is going to be transmitted over one overhead line. That is also vital, because you can see some of those flicking through in the spot, saying that there is what they call a chicken neck, which is an area, a valley between two mountains. It's only 22 kilometers in between. And it's very hard to build AC lines on this. Normally we would need, in a conventional system, we would probably need 4 or 5 AC lines for the same amount of power. Instead, we can use this with one. That's one of the benefits of this type of systems. So 6,000 megawatts, but it can be overrated to 8,000, and it's going to be used for 8,000 megawatts when they have expanded the hydropower plant. So 8,000 megawatts, 800 kilovolts over 1,700 kilometers. Right now, we are looking into 1100 kilovolts, ultra-high HVDC, which is the next step, to be able to transmit even more power. So this is the trend. This is where we are going with this. And as you can see, it is phenomenal phase. Not only producing the equipment for that, but actually installing it, operating it, so on. Another thing you can see with this is that it will only have less than 6% losses with this type of amount of energy over this distance. Again, compare this to normal AC line, we would probably lose something like 25% along the way. Losses in terms of heat, in the connections, and so on and so forth. Here, less than 6%. And of course, when you're talking about 6,000 or 8,000 megawatts, this is a lot of money in the end of the day that we can save. Again, energy efficiency. So this was basically what I was going to cover in this, of our journey. As I said, there is a lot of many other things, of course, that we have done and which we are proud of, in the same way as we are proud of what we have achieved so far. But we are by no means happy with that. We want to go further than this, of course. Thank you.
Thank you, Mr. Holmberg, for this very interesting overview of the history. So we have now got a few questions. So first one would be, how green is ABB innovation? How do we measure it?
How green is innovation? In what terms? I mean, how green is how we're doing it, and how, I think everything we have today, I mean, to be green today is a bit of a buzzword in many aspects. Everything should be green. We think energy efficiency is green because energy efficiency, as you saw, we can actually help to achieve, to reach the CO2 targets that has been put up. So in that sense, it is green. We don't want to greenwash the company as such, but in a way we can say that we are a green tech company. If we are allowing ourselves to be a little bit more freely in that. How we're measuring it? Well, we're measuring it on product. I mean, we can say that by installing certain types of equipment, we can save equivalents to this and that in terms of CO2 or in terms of energy savings and so forth. I have no figures of that, but you can almost see that in every product presentation. That if we are doing this, we can save such and such, which is equivalent to 180 cars for a year or something like that. But it's difficult when you, I mean, you have to talk about equivalence because otherwise it gets very difficult to do that. I don't know if that answered your question as such. You have to come back to afterwards or something like that. We can develop that.
Okay. Then we have another question, which is actually quite interesting when we are looking through this history line we just saw before. Then the question is, for the future, which products could be ABB main products in 2030 or 2050?
Well, I think, I mean, we're allowing ourselves to be a little bit visionary here today, so I think we'll see perhaps one of them later on from Anders. Who knows? But I think HVDC will continue. The facts will definitely continue in that sense, because when we're talking about being able to increase capacity on existing lines to transmit bulk energy and so on, that will be definitely something for the future. But there are all the others. There's a lot to do in the industry. Extended control system, for instance, is one of them. Robotics is another one. We have the variable speed drives. You know, we are doing them more efficient. We're coming up with new things all the time. We have a lot of invention which we don't go forward with because we find the market is not there. And we have been through a couple of those over the years as well. Things which probably have been great today, but at the time they were not there sort of at that time. So I think out of our main products, I think most of them will still be there.
Okay, thank you. Thank you very much.
Thank you.
I'm afraid our time span is now pushing us. Mr. Holmberg, just a moment. Would like to give you a gift also. Thank you very much
Thank you very
once
much.
again.